What if the universe has been quietly telling us we ray wrong and we just learned how to listen? For a century we've stitched together a grand story. The Big Bang expansion, the first stars, the slow rise of galaxies, and a cosmos governed by elegant equations. Then, the James Webb Space Telescope opened its golden eye. What it found didn't just add a new chapter. It began tearing out pages and scribbling in the margins. Galaxies that shouldn't exist yet. Black holes that grew too fast. A cosmic expansion rate that depends on how you measure it. And signals and visitors that force us to ask whether we're seeing deep physics, rare coincidences, or hints of something even stranger. Tonight we're going to separate the panic from the planetary science, the hype from the hard data, and follow the breadcrumbs Webb has scattered through the dark. By the time we're done, you'll understand why many astronomers now say the universe is more complicated, more dynamic, and possibly more cyclical than we ever imagined. The promise: this isn't about dunking on the Big Bang or cheering for wild theories. It's about what the data actually show, what they might mean, and why the next few years could rewrite the cosmic playbook. We'll walk through the anomalies, the best conventional fixes, the bold alternatives, the risks of getting fooled, and the plan to decide fast before the window closes. The map we thought we knew. For decades, the standard model of cosmology, often called CDM, has been the backbone of our understanding. A 13.8 billion-year-old universe, seeded by quantum fluctuations, inflated in its first moments, then cooled into a cosmic web where dark matter scaffolds galaxies and dark energy drives faster and faster expansion. Only 5% of the universe is normal matter you can hold, burn, or breathe. The rest is invisible bookkeeping that makes the equations balance and the sky match our maps. Under CDM, structure unfolds methodically. First, hydrogen and helium. Then, a few 100 million years later, the first stars ignite. Hot, massive, short-lived galaxies assemble slowly within dark matter halos. Star formation ramps up, black holes feed, and reionization, the great clearing of the hydrogen fog, spreads across the cosmos. By about a billion years after the beginning, by our time, gravity has had eons to sculpt spiral disks, barred bulges, and the vast filaments that funnel matter into clusters. But this tidy arc has always had splinters. Rotation curves implied missing mass. Supernova distances implied accelerating expansion. And in recent years, a growing crack. Two incompatible measurements of the universe's current expansion rate. The Hubble tension. One method calibrates a distance ladder using Cepheids and type a supernova and lands around 73 kilometers SMPC. The other reads the early universe imprint in the cosmic microwave background and backs out a lower 67 km SMPC. Both are careful, modern, and precise. They just don't agree. Enter Webb. Shock and awe, Webb's first surprises. James Webb sees in the infrared exactly the light that ancient galaxies have had stretched into by expansion. That makes it a teamy machine aimed at the cosmic dawn. The expectation: faint smudges, proto-galaxies just beginning to assemble. The reality: some of Webb's first deep fields revealed compact, surprisingly luminous systems just 300–500 million years after the Big Bang. Follow-up spectroscopy confirmed that at least several of these are really that far back. Even more provocative, a subset look mature for their age, red, dusty, or already enriched with heavy elements. A few host active galactic nuclei, implying substantial black holes already in place. And elsewhere in Webb's reionization surveys, astronomers found strong Lyman alpha emission escaping earlier than expected, which hints that the fog of neutral hydrogen cleared in pockets surprisingly fast. None of this instantly kills the standard model, but each data point shoves in the same direction. The early universe may have made stars and black holes faster, more violently, and more efficient lie than our default recipes allowed. A second drumbeat came from galaxy counts and brightnesses. There seem to be more luminous galaxies at the highest redshifts than many models predicted. Some early photometric claims were walked back. After spectroscopy, false alarms are part of frontier science, but the pattern of robust cases remains. The universe was industrious very early. Overlay that with the ongoing Hubble tension now. Checked again with Webb's sharper Cepheid id work, and the unease grows. If the late-time expansion is really faster than what the early-time CMB implies, then something in our cosmology must evolve, or we're missing a subtle bias somewhere. Either way, it's not nothing. And yet, Webb isn't just catching outliers, it's also revealing the mechanisms that could plausibly drive such behavior. Burst seeds and shortcuts. One fix doesn't require exotic physics at all. Bursty star formation in the dense street early halos. Gas can crash, cool, and ignite in brief, furious episodes that dramatically boost luminosity and metal enrichment. Simulations that include strong feedback, clumpy inflows, and top-heavy initial mass functions can manufacture short-lived, ridiculously bright phases. If Webb preferentially catches those fireworks, we'd naturally overcount massive early galaxies unless we correct for the burst. Another pathway, direct collapse black holes, instead of building every supermassive black hole from countless stellar corpses. Some environments metal poor, intensely irradiated, dynamically quiet, can skip steps, collapsing a huge gas cloud straight into a black hole seed of 1010 solar masses. Feed those seeds well, and suddenly the too fast quasars look less impossible. On the dark matter side, if the particle isn't perfect like cold and collision, let's say it is lightly warm or mild lie, self-interacting, the small-scale assembly can change just enough to alter early halo formation and star formation histories. You still keep the large-scale web, but tweak the timing and efficiency at the smallest scaffolds where the first galaxies hatch. Then there's early dark energy, a transient injection of energy density around recombination that fades later. It can reconcile the CMB with our local Hubble constant without breaking everything else. It's a delicate dance, and it leaves telltale ripples that upcoming surveys can confirm or rule out. In other words, you can, with some effort, bend CDM without breaking it. The bold alternatives, but Webb has also poured fuel on bolder ideas. If you're willing to reconsider the very bookends of cosmic history, you land on frameworks like conformal cyclic cosmology. Roger Penrose's proposal that our Big Bang was not a beginning but a transformation from the infinite future of a previous eon. In such universe, all matter eventually decays. Black holes evaporate via Hawking radiation, and what's left is a zeta of radiation that can be conformally mapped to a new, smooth Big Bang. In that case, some subtle patterns, circles, or hotspots in the microwave background could be fossils from a prior cosmos. Claims of those signatures are controversial, but Webb's knack for exposing early structures emboldens people to ask whether time has a longer memory than we thought. Others look to multiverse ideas from inflation, where pocket universes bud with slightly different settings, or bounce models where contraction precedes expansion, or even preferred direction hints like the CMB, cold spot, and axis asymmetries. Most of these are speculative and testable only indirectly, but every time Webb finds a galaxy too soon, the appetite for alternatives grows. Two eyes on an interstellar visitor. While cosmologists argue over first light, Webb and Hubble have done something unprecedented closer to home. Watch an interstellar object together, after Oumuamua and Borisov. A third visitor nicknamed 3i Atlas arrived from deep space, bright enough for coordinated scrutiny. Hubble's crisp optical imaging traced the coma and dust behavior. Webb's infrared spectra probe bed ices, organics, and silicates, the raw recipe of a world formed around another star. Some quirks popped up, activity at unusual distances, dust that didn't blow away as easily as expected, a tail geometry that hints at heavy grains, and an orbit slicing retrograde but only slightly off the solar system's plane. Odd but not impossible. Does any of that scream artifact? No, natural comets are messy, diverse, and full of surprises. But 3i Atlas gives us something we've never had: a full spectrum profile of an interstellar traveler observed in real time, with two great observatories at once. If it behaves oddly around the sun, we'll see it. If it hides shocking chemistry, we'll catch it. And if it just acts like a comet, that's a good constraint on what interstellar normal looks like. Panic procedure and a planetary near miss. Webb also arrived at a moment when the world needed to remember how planetary defense truly works. A newly discovered asteroid, let's call it the kind we worry about, can debut with scary preliminary odds. With only a handful of positions on the sky, the cone of uncertainty is huge, sometimes including the Earth. Impact probabilities can rise before they fall as we fill in the orbit. That's not incompetence, it's geometry. The Torino scale was invented to communicate that process. Most things are a 0 or 1 routine, no danger. A few rare cases briefly tick up to a 2 or 3, worthy of attention and more tracking. And then, almost always, they drop when global networks of telescopes coordinate. That cone collapses, the error bars shrink, and the odds fade to background. Occasionally, we model lunar impact scenarios reminder that a hit on the moon would be dramatic but not dangerous to Earth. Ejecta-cooled pose risks to satellites if trajectories were just so. But the larger lesson is quiet and powerful. The system works: early warning, rapid follow-up, and sober communication beat viral panic every time. The night side of a neighbor. Speaking of sober, the search for techno-signatures is maturing. One intriguing idea proposed long before Webb launched is to look for artificial light on the night side of nearby exoplanets, especially tidally locked worlds where a permanent hemisphere hides from starlight. If a civilization lights its cities, the spectral fingerprint of LEDs or other sources could in principle be detectable with deep, clever observations. Proxima b, our nearest potentially rocky neighbor, is the poster child for this thought experiment. It hugs a flaring red dwarf that bathes its dayside in harsh UV and X-rays, like lime, making the Terminator zone, the twilight belt between day and night, the best refuge for liquid water. Some reports have teased unusual infrared glows or periodicities from the dark hemisphere. Are they artificial? Almost certain lie, not at least. Not based on current data. Air glow, or atmospheric circulation, volcanic hotspots, or dust scattering can all produce structured, time-varying emission. Webb's MIRI instrument and ground-based giants will keep probing, looking for non-thermal, narrow-band features or modulations that scream technology. So far, no clear techno-signature. That's not a letdown. It shows you do this carefully by ruling out natural false positives one by one. Meanwhile, Webb's exoplanet work has already hinted at BIOS igniture chemistry elsewhere, like methane and carbon dioxide in the atmosphere of K218b, and even a tentative whiff of dimethyl sulfide, a molecule tied to life in Earth's oceans. Those claims are actively debated. Data are hard, models are brittle, and we'll need multiple instruments to confirm. But the point stands. For the first time, we reign not just imagining exolife. We Ray building the tool chain to find it, if you want to be here when those answers arrive. When Rubin catches the supernova, that finally pins the expansion rate. When Roman Slensing maps light, up dark energy's fingerprints. When ELT weighs a black hole seed in the active B. Coming Aquasar, stay with us. Subscribe, leave a signal, and tell us which clue you want us to chase next.